All right, welcome to week three's material. In chapter three that we're going to look at now, they're going to give us some applications of radian measure. And if you remember how we defined a radian, its actual definition is related to arc length. And when we defined the radian back in section 3.1, part 1, it was defined to be you would have 1 radian if you swept out an arc equal in length um, to the radius, right? And that was the definition of 1 radian. And so we use that to get this definition of arc length. The length s of an arc intercepted on a circle of radius r by a central angle of measurement theta, radians, is given by the product of the radius and the radian measure of the angle, or S is equal to R times theta. So that's a lot of words to say something that's very, very nice. So let's just produce an angle theta here. I'm going to switch my color to blue. And I'm going to come in here and I'm going to put an angle theta. What if we look at the definition, and it's this definition that I want to look at here. S is equal to R times theta. And it's important that you see this. It's bolded and somewhat italicized. Theta is in radians. That's what makes it a nice clean formula. If it's not in radians, we have to do the conversion, but you know that conversion of pi over 180. And so let me put some symbols in here. Remember, S is equal to, and now I will use different colors because I can, R times, and we'll use black, theta, right? And so what is R? R is this distance right here, as it always is. It's the distance from the center to the edge of the circle, right? What's S? Let me put S in the picture in blue. S is this picture right here. This right here, this arc length right here, I was going to put an arrow on it, but I shouldn't. This is what they're referring to as S. That's the arc that swept out. And there's lots of things that happen in a circular pattern, and so the arc length is something that we are very interested in. And theta is for sure just the angle there. So it's just simply R times theta. You'll need a calculator for this section because if you notice, even in the first example, they want you to round to the hundredths place, right? And they give you things there. So note that in degrees, the arc length formula is S is equal to theta over 360 times 2 pi r. Now that seems a little bit crazy, right? It actually makes more sense here, where remember what S was equal to R times theta if theta is in radians. If theta is in degrees, well, that's R, and you got to convert the degrees to radians by multiplying by pi over 180. So this latter formula makes sense from a conversion ratio. But here's the reason why they're showing this one. 2 pi r is the circumference of a circle. Notice if you go all the way around, the arc that swept out should be the circumference. If you go all the way around, this is 360 degrees. If you go all the way around in radians, it's 2 pi. So it's all interconnected. The circumference being 2 pi r, and this whole formula is all meant to just have you say, oh, holy cow, it does work. Okay, so let's take a step back. What's the big thing that was said? The biggest thing that was said, and what we're going to use, is that S is equal to R times theta if theta is in radians. And if it's not, we're going to have to put it in radians. So let's go watch that work. So if we look at this example number 1, which will match many examples in the book, it says a circle has radius 25.60 centimeters. Find the length of the arc intercepted by the central angle. A central angle goes right through the middle. Having each of the following measures. 7 pi over 8 radians. They didn't have to write radians. No units means radians. But here's all they're asking us to do. They want what? They want the length of the arc. They want S. So S is equal to R, given to me, 25.60. And radians. given to me, 7 pi over 8. And so we're going to grab our calculator and we're going to type in 25.60 times 7 times pi divided by 8. And we're going to get an answer there. So, I'm not, sorry, not, oh yeah, divided by 8. I had mistranslated it in my notes. And so we're going to get an arc length of 70.37. 70.37 what? 70.37, not radians, it's not a degree, it's a length. It's a length along the circle that has a radius of 25.6 centimeters. This is all in centimeters. Make sure to put the units on there. Now over here, let me grab an eraser so I can move this. We know that S is equal to R times theta. So S is equal to R, still 25.60 centimeter circle. And our theta is 54 degrees, but I got to change that into radians. And if you remember, we multiply by pi over 180. And so you just plug in 25.6 times 54 times pi divided by 180, and you get a nice 24.127. So you'll report 24.13, and again centimeters. Pretty nice. So we have some formulas or some problems that just give you familiarity with the formula. And then they're going to require us to think. Look through some situations and be able to think through them. And so we have Erie, Pennsylvania is approximately due north of Columbia, South Carolina. The latitude of Erie is 42 degrees north, while that of Columbia is 34 degrees north. Find the north-south distance between the two cities. And in order to do this, we would have to recognize that we're on the Earth. And the Earth isn't flat. It isn't a rectangle. It's a circle, right? It's a sphere, I guess, but it's circular in nature. And we're traveling up that latitude line. So here's our Earth, right? And we're going up one particular latitude line. Well, that's an arc length. That's not a straight, up and down distance. We're going to have to use the arc length formula. No problem. Luckily, they gave us the radius of the Earth in kilometers, but that's great. So let's take a look at it. So what do we know? We know that one of the cities is 34 degrees north, right? So there's 34 degrees north of a center line. And the other one, let me do that in a different color, is 42 degrees. And now make sure you see where the 42 is. The 42 is from the horizontal line up to here. Well, what do we care about? If I break out this picture, and let me do that to the right, I'll get rid of my Earth that looks pretty lame, and I'll come in here, and if we break out this picture, what we're concerned with is this movement right here. We need this arc length. We need this S. That's the S that we need. As we move from the 34 degree line to the 42 degree line. Well, how much is that? So let me come in here and write these letters a little bit more clearly. This is what we're after, S right here. That degree sweep right there, I'll put in red. That's the one that we want. Well, it would be the 42 degrees minus the 34 degrees for an 8 degree sweep. We want to know what's swept out with 8 degrees because that will give us that arc length, which will be the north-south distance between those two cities since they're due north of one another. No problem. What we know is that S, what we want to find, is equal to R times theta. They give us R in kilometers as 6,400 kilometers. And we just found that we're doing an 8 degree movement on that circle. We're going to have an 8 degree sweep. Well, I don't want degrees. So I'm going to have to multiply by pi over 180 degrees. So my degrees cancel out. And I'm left only with kilometers. That's why radians are preferred, is they have no units. They're just a real number. So if I look at 6,400, and you don't have to do any reduction. You have a calculator, and you're going to need it anyway. Times 8 times pi divided by 180. I'm going to find out that they're 893. And do they tell me how to round? They don't tell me how to round, so I'll just do the same as what we did last time. And I'm looking at 0.608. So I'm going to do 0.61 of a kilometer. So 893.61 kilometers is how far those two cities are away from each other from a straight north-south distance. Doesn't mean that that's what we're going to be able to travel, right? We're limited to roads and things. So they give other applications. You'll see a rope right here being manipulated around, and then also gear movement. So two other applications that are here. And so feel free to pause the video whenever you need, but this should give you the rough ideas of how to approach each one of the homework questions. So let's see what's happening here. A rope's being wound around a drum with a radius of 0.327 of a meter. How much rope will be drawn around the drum if the drum is rotated at an angle of 132.6 degrees? Now, what's important, and I'll just talk to you, you're good math students. This is not a full rotation, which is important. If it was more than a full rotation, at some point we'd have to recognize that that rope might overlap it and we have a different radius going on. That's later, right, when thinking through those. But this rope is going to be pulled around a drum. And so essentially it's just going to be wrapped around this center piece, right? So if that's my drum right there, I'll make it look like a cylinder. This rope that I'll put maybe in black is going to wrap itself around this. So you can see that we're going to get an arc length out of that as that drum rotates. And so this is nothing more than an arc length problem. We know arc length. S is equal to R times theta. So what's the radius that it's going around? 0.327 of a meter. And its degree is 132.6 degrees. So they're giving everything kind of in degrees, it seems like. Well, that's the most amount of work, so that's good that we're practicing with it. And what we end up with is an arc length all in terms of meters. So if I take 0.327, multiply by 132.6 times pi divided by 180, just doing that calculation with you, we get 0.7567. Okay, so 0.327, 132.6 times pi divided by 180, and I'm looking at the number S is equal to 0.7567. So I'll do 757 of a meter. Okay, something like that. So last problem that is related to arc length, and then we're going to get to one problem that they have at the end of it, just playing around with the formula, the area of a sector. So this one is a little bit more involved because we have two gears. So two gears are adjusted so that the smaller gear drives the larger one, as shown in the figure. If the smaller gear rotates through an angle of 150 degrees, through how many degrees will the larger one rotate? And so let's talk about that. So the first thing that we're going to need to do is find out how far this small gear moves, because that will be the same movement as this guy. That will be how far this one moves. Or the arc that it sweeps out. And so if I can know that, then I can find the angle. So the first step is to find out the rotation on the small angle. So let's do that. I'm going to erase what I wrote here. It's a very small area to work in here. And it won't work very well if I go off to another note system. So let's look at this small one. The small one, and I'll do the work right over here so I leave this big blank. We know S is equal to R times theta. What's R? 3.6. What's theta? 150 degrees. So we're going to multiply by pi and divide by 180. And we're used to that by now. And so when we take our 3.6 times 150 times pi divided by 180, we get 9.424. So I'm going to put it as 9.4, the same level of rounding that the radius was in. So this thing moved 9.4 inches. Well, so did the big one. So did the big one. So it just moved less of an angle through, and that's what they're asking for. So this is the small, and now let's go to the big. So as I go to the big, I'll do it in a different color. So let's go look at the big one. Well, what we know is it traveled 9.4 inches. And we know its radius is 5.4. But we don't know the angle that was moved. And so we just solved this. This is 9.4 divided by 5.4. And we get 1.74 is equal to theta. Now, what is 1.74? I'm hesitating for a reason. If you're using the S is equal to R times theta, what's the degree always in? Always in radians. Never in degrees. That's a radian measure. So what do I need to do? I need to go back to my old chapter 1. 3.1 idea. Apologize. It's in 3.1 that we were introduced to radians, and we need to convert this to degrees. Well, hopefully you remember how to do that. That's the flip of what we've been doing. The 180 on top and the pi on the bottom. That will convert it to degrees. So I take my 1.74 that I got just by simple division. And if they let me leave it in radians, I'd be done. But they want it in degrees because they say how many degrees. And so nice conversion practice. And if we just follow that times 180, we get 99.7 degrees. Almost 100 degrees. So when one rotated 150, the big one only had to rotate 100. And it'll get more dramatic as time goes on. The last thing that's presented in this section, I think it's right at the very, very end, and we just want you familiar with this. It's the area of a sector. And it says a position in there to prove it. I don't think we need to spend our time doing that. But let's talk about what they're meaning. If this is R and this is theta, again, theta in radians, I'll come in here with the highlighter. This inside area right here is what they're referring to as the area of the sector, this kind of cone-shaped area. And you can see that it's based in a triangle, but also based in a circle. So the formula makes a whole lot of sense. The 1/2 coming from the triangle, the r squared coming from the pi r squared that's there as you work through a circle. And so you're just going to have to find the area of a sector. I don't believe there's any crazy problems in there. They just want you familiar with the formula. Has a little fancy A, right? I'm not going to be able to do that, so I'll just put an area of a sector. And the area of the sector is 1/2 the radius squared. Well, what's my radius? They give it to me as 15.20 squared. And times the angle. And the angle in this case is 108 degrees. So I got to multiply by pi and divide by 180 degrees so that my degrees cancel out and I'm left with the right units. Okay, or that I get it into the radian mode. So if we look at 1/2 times the 15.20 squared times 108, I read that wrong, times pi divided by 180, just walking you through that calculation, you get 217.75. Now, what's the right unit? The radius was in feet, so the unit's feet. But if you leave that, I'll most likely take off a point on your exam because this is area and should be square feet or feet squared. That is what we're dealing with. Units you've been playing around with for a long time. So if I come back here, let's make sure everybody has a unit. Degrees, inches, right? Just a straight linear measurement of how far things went. But it was actually that end answer. Meters, yeah. The length of that one. And so you can see that each one of those has the appropriate unit. So make sure that that's part of your attention to detail in there. And then these should serve as decent examples, but hit me up with any questions that you have, either through email or via the Zoom, and I'll respond. Thanks.